In part 3 of this video lecture series, we will discuss the derivation of velocity equation of the entire Hooke's joint. Now, in the previous part, we have derived the displacement equation of the entire Hooke's joint, which is tan of the input angle rotation is equal to cos of the angle of the shaft between the input and the output multiplied by tan of the output angle shaft. So, theta and phi are the input and output angles rotated. They are continuously changing. Shaft angle is alpha. Now, for the notation wise, let's assume omega 1 as the angular velocity of the input shaft. This angular velocity of the input shaft is constant. So our input shaft is constantly rotating at say same speed, and mathematically derivative of theta with respect to time, derivative of position with respect to time would give you the angular velocity. Similarly, omega 2 could be defined as angular velocity of the output shaft. Now, the output shaft does not rotate with a constant speed. This is something which we will prove it by deriving. Now, what we need to derive in this part 3 is a little bit mathematical, more of differential analysis of derivation of the position equation with respect to time. So if you differentiate this first equation with respect to time, in physics it simply means differentiate your position with respect to time. So obviously we would get velocity. So left hand side has a tan theta. Derivative of tan theta would be a sec square theta. Derivative of theta in turn with respect to time would give you a d theta. That's it. Right hand side, the shaft angle alpha between the two is constant. So cos alpha remains as it is. Derivative of tan phi would give you a sec square phi d phi by dt. Now, this d theta by dt is nothing but angular velocity of the input shaft, and d phi by dt is nothing but angular velocity of the output shaft. So, if you rearrange the terms, you will get sec square theta into omega 1 is equal to cos alpha into sec square phi into omega 2. Now, I will simply write this as a ratio of output velocity in the numerator divided by input velocity in the denominator. This would give me an equation. Sec square theta would remain on the numerator. Cos alpha sec square phi would go in the denominator. Now, in my opinion, actually so much amount of physics and ye should be enough for engineering students to understand. This is actually the output velocity equation, because input velocity omega 1 is constant, that will be given to us. Now, if you carefully notice on the right hand side, we have three variables. Alpha, the shaft angle between the two, is constant. So we don't have to worry about this term cos alpha. Now, it may be noticed that as the input shaft theta rotates and theta changes from 0 to 360, corresponding output shaft angle phi will also change from 0 to 360, but they are not the same. They are not the same because they are not in the same line. If they would have been in the same line, they would have rotated together. Now that they are offline, this rotation of the input theta and output phi will have some phase lag. The mathematical relation between theta and phi is the equation number 1. So now henceforth, the trigonometry involved in this case is to somehow reduce this right hand side and get it only in terms of theta. In layman terms, we could say somehow replace phi and get these terms in terms of theta. Now, a simple mathematical adjustment, if you notice, we could replace sec square phi by 1 plus tan square phi. This is basic trigonometry. Now, tan phi, as from the first equation, is tan theta divided by cos alpha. What we want is tan square. So, tan square phi would be tan square theta divided by cos square alpha. So, what we could write as numerator sec square theta as it is, cos alpha as it is, 1 plus, we would replace this tan phi by this tan phi by tan square theta divided by cos square alpha. Now, this becomes a very easy equation to understand. Notice that we have got rid of phi. There is only theta, theta, alpha and alpha. Out of this, alpha is a constant. We don't have to worry about this. Now, we can just, in small steps, I will just show how we can modify this and make it in a form which is very easy to remember. So, let's focus only on the right hand side. Let sec square theta remain as it is. The cos alpha from outside remain as it is. Let us replace this tan square by sin square theta upon cos square theta, cos square alpha as it is. Now, a little bit of algebra involved here would say that if I take the LCM inside the bracket, we would get sec square theta as it is, cos alpha, you would have a cos square theta cos square alpha plus sin square theta, divide this by cos square theta cos square alpha. So I have done nothing but I have taken this LCM inside the square bracket. Now, this entire denominator can be shifted here. So my next step would look like sec square theta as it is, cos square theta, sec square theta as it is, cos square theta cos square alpha from the denominator go up, and cos alpha cos square theta cos square alpha plus sin square theta would remain as it is. Notice that sec and cos are reciprocal functions of each other. So sec square and cos square I am cancelling because it is upon 1, the product is 1. Then 1 cos alpha from the denominator can always be cancelled. We will be finally left with a simple cos alpha in the numerator, cos square theta cos square alpha in the denominator, and sin square theta in the denominator. Very carefully, if you notice, this equation here and this is all exactly the same. We are just trying to rearrange and get them in a simpler format. Now, by simpler format I mean, it doesn't matter where alpha comes because alpha is always a constant. It will be given in a problem. We are trying to adjust this term theta such that theta does not appear twice. Theta comes only once in the total formula. Now, how we do it is very easy trick in trigonometry. Keep the cos alpha as it is. I want to adjust these two terms, and to adjust these two terms, the trick in trigonometry is cos square alpha can be replaced by 1 minus sin square alpha, and do not disturb these two terms. Notice that actually we wanted to adjust these two terms. They are still as it is. What we have adjusted is alpha. It will be very clear to you in the immediate next step. Now, cos alpha as it is. Now, when I open the terms and take this inside here, I will get cos square theta minus cos square theta sin square alpha, which is this term, and the third and the final term of sin square theta as it is. Now you will appreciate why we did this is because now the cos square theta term and the sine square theta term can be grouped and we will get a 1. So therefore finally angular velocity ratio of the output shaft upon the input shaft speed can be written in a very simple format as cos alpha in the numerator 1 minus cos square theta sine square alpha. And this, if you notice, is a very easy velocity equation of the entire Hooke's joint to remember. End of part 3.